Hi everyone, welcome back. In this video we're going to examine the final type of kind of more complicated kinematics problem that we're going to examine using the skills of algebraic kinematics that we've been developing. So this is a situation where we're dealing with multiple accelerations. Now, in each segment, the acceleration is constant, but there are multiple segments, each of which have a different value for the constant acceleration. So, as before, let's look at an example and see how we deal with something like this. So we have a bus starting from rest, accelerating from to 10 meters per second at a rate of 2 meters per square second. And then the bus shifts gears, accelerates at 0.5 meters per square second for the next 8 seconds. And then after that, it comes to a stop in 30 meters during the third segment. How much time did the trip take? Well, we can get some intuition about this by drawing a velocity versus time graph. So let's see how that looks. During the first segment, we have relatively rapid acceleration. Notice a reasonably steep slope there. Then during the second segment, it's still a positive acceleration, but velocity versus time graph, slope is acceleration. It's a smaller acceleration, so it's positive but smaller, so we have it as a more gradual slope. And then it comes to a stop in 30 meters. Now, I don't know whether the slope on this final segment is correct, but in any case, if somebody was to, say, take the area under this part, that area should end up being 30 meters. So now that we have kind of an idea of what's going on here, let's think about how we're going to tackle this problem. Notice that at the end of each segment, there's a new velocity, which means that velocity at the end of each segment is going to be the initial velocity for the beginning of the next segment. That's very important to keep in mind. So really what we're going to be doing here, since there are 3 different slopes, that is 3 different accelerations, we're going to have 3 different columns. We can call them column 1, column 2, column 3. However, in fact, generally speaking, when you do this, you should probably use subscripts for your individual accelerations. For example, I would call this, well, v naught is fine, and calling that 0. And then I would say v sub 1 is 10 meters per second. And then v sub 1 becomes the initial velocity for segment 2, and v sub 2 becomes the final velocity for segment 2. A sub 1 is 2 meters per square second. And delta t2, and it's probably better to call this delta t sub 2, is 8 seconds. Delta t sub 1 right now is unknown. A sub 2 is 0.5 meters per square second. And again, our final velocity for the previous segment becomes the initial velocity for the next segment. Though if you want to be consistent with subscripts, I would probably call this v sub 1, and again, say that the final velocity is v sub 2 there. And then that v sub 2 would become the initial velocity for segment 3, but v sub 3, the final velocity for segment 3, is actually given. It's 0. And we're also told that delta x for segment 3 is 30 meters. And here we probably should call that delta x just to make sure that there isn't any possibility of confusion. Well, in order to figure out what the initial velocity for segment 3 was, we need to figure out what the final velocity at the end of segment 2 was. So that's where our v equals v naught plus at equation comes in. So we have v naught, well, actually really probably better to call it v sub 2 equals v sub 1 plus a sub 2 times delta t sub 2. But in any case, we have that our initial velocity for segment 2 was 10 meters per second. The acceleration there was 0.5 meters per square second, and the time interval for segment 2 was 8 seconds. And that gives us a v sub 2 at the end of segment 2 of 14 meters per second. So that becomes our initial velocity in segment 3. And then you could calculate everything in terms of the times to figure out how it ends up going. So, well, we know what v and v naught were for segment 1, and we're just interested for the time. The v naught there was 0, so we just have that delta t1 was 5 seconds. We're already told that delta t2 was 8 seconds. That was part of our givens. What about delta t3? So we're not given any value for the acceleration here, but we could use our v average equation. That is delta x over delta t equals v naught plus v over 2. Or in this equation, it would really be delta x3 over delta t3 equals v2 plus v3 over 2. But in any case, Once you do that, you're going to end up with a time of 2.143 seconds at the end of segment 3. So when you add together all three of those time intervals, you get a total time for the trip of 15.143 seconds. So just showing our work on that, there's the equation, in this case using proper subscripts. And since v sub 3 is 0, our final velocity for segment 3 is 0, we eliminate it. And we're trying to solve for delta t3, so we do a little bit of, we flip both sides of the equation first to get delta t3 over delta x3 equals 2 over v2, and then multiply both sides by delta x3. And that's what we get. Plugging in our numbers, we then get 2.143 seconds. So again, when we add them up, we get a total time for the trip of 15.1 seconds, just rounding to 3 sig figs. Let's take a look at another example. A car starts from rest, accelerates at 0.5 g's for 50 meters, and then travels 8.52 seconds at constant velocity, then slows down for 3.12 seconds with an acceleration of negative 2.50 meters per square second. What's its final velocity? What was the total distance traveled? And what was that final acceleration in g's, just out of curiosity? So, again, we have 3 columns, which means 3 different sets of givens. So we have the initial velocity for segment 1 is 0. The acceleration for segment 1 is 0.5 g's. Whoop, we got to convert that to SI units. That's 4.9 meters per square second. And the displacement in segment 1 was 50 meters. That's just straight from our givens. And then for segment 2, delta t2, I really should have a delta in front of there, is 8.52 seconds. And the acceleration for segment 2 is 0 because it's going at constant velocity. And then for segment 3, the delta t3 there is 3.12 seconds, and the acceleration for segment 3 is negative 2.5 meters per square second. So now we have our givens. So let's figure out everything we can figure out in segment 1. So those were our givens for segment 1, nothing new now. And we want to figure out the final velocity at the end of segment 1. So, well, v squared is v naught squared plus 2a delta x. So v sub 1 squared is v naught squared plus 2a sub 1 delta x1. So find what v sub 1 is. Well, v sub 1 squared is 490. Take the square root of 490. You get about 22.14 meters per second. And that's the initial velocity for segment 2. Or I could just call it v1 and call the final velocity for segment 2 just v2. Either way is fine. So the acceleration in segment 2 is 0, which means the initial and final velocities there are the same. We don't know the displacement for segment 2. So, well, think about an equation that has displacement in it and everything else in the equation is in our givens. Well, we have initial velocity and final velocity. Acceleration is 0 and we have time. So how about just the delta x equation? And the 1/2 at squared term is 0. So that's an easy calculation there. So we get the displacement in segment 2 is 188.598 meters. Remember, don't round until the end. So I'm just kind of keeping some extra digits there so people can keep track. For segment 3, we already got that the final velocity at the end of segment 2, which was the same as the final velocity at the end of segment 1 since acceleration in segment 2 was 0, is 22.14 meters per second for the initial velocity of segment 3. The acceleration for segment 3 is given, and the time passage in segment 3 is also given. So how about figuring out the final velocity in segment 3? That was one of the things we needed to do. Well, v equals v naught plus at. We're asked for final velocity, so we need an equation that has that. Everything else in the equation needs to be in our givens. Well, the v equals v naught plus at equation works. So v sub 3 is v naught 3, or you could just call it v sub 2, plus a sub 3 delta t sub 3. Plug in the numbers, and you get the final velocity in segment 3 of 14.3 meters per second. And then the displacement in segment 3 can be found using those same givens. V naught, a, and t are all given. So there's our displacement in segment 3, about a little shy of 57 meters. So now we get that the entire displacement for the whole trip, just the sum of the individual displacements, delta x1 plus delta x2 plus delta x3, turns out to be 295 meters. What about the acceleration in g's? Well, that's just a unit conversion, and when we do that, we get negative 0.255 g's of acceleration. So that is how we solve a segmented kinematics problem. Just kind of going back, notice that we set up several different segments we first wrote down all of our givens, and for each segment, we figured out everything we could possibly figure out. How far it went, the time that passed, and the final velocity. We used the final velocity for each segment as the initial velocity for the next segment. Figured out everything we could for the next segment. Some things are already given, like the time passage, but we needed to figure out the displacement during that segment. And then, again, the final velocity of segment 2 is the initial velocity of segment 3. Figure out everything we can in segment 3, including final velocity, displacement, etc., and then add together all the displacements to get the displacement for the whole trip. If we wanted to, we could have added up all the times for the 3 segments to get the travel time for the whole trip as well. So, again, the idea is find the number of regions having different accelerations. Generally, it's going to be 2 or 3. For each region, give it a number or a name or something like that. And in the first region, find all of the kinematics quantities that are true in that region. The displacement, the final velocity, the time passage, etc. And then, for the next region, you can kind of imagine beginning afresh with an initial position of 0 and an initial time of 0, and then use the fact that the final velocity at the end of this last segment is your initial velocity of your new segment. And as with all of the other kinematics problems, keep in mind keywords like stops, decelerates, constant velocity, maintains previous speed, etc. And then, after the final region, add together all times to get a total time, add together all displacements, I should say add together all displacements to get a total displacement. Here where I say final positions, we're imagining that we begin each segment with an initial position of 0, in which case we're still just calculating a displacement. So, I hope this has been helpful for allowing people to figure out how to solve different types of kinematics problems in this series of 3 videos. And if you have any comments or questions, then please leave them in the comments box on YouTube. And the next unit will be how acceleration happens in the first place. Where does acceleration come from? That's where we're going to encounter forces and Newton's laws. Until then, I'll see you later. Thanks for watching.